Hello, this is Mr. N, and we are doing our second review for the Chapter 3 test, the one that covers 3.1 to 3.4. And let's go ahead and go through these problems. On the first one, it says find the average rate of change of f of x on this interval. Remember, when we need an average rate of change, it always happens on an interval. So in this case, what I want to do is I'm going to take my f of 3 value minus the f of negative 2 value over the 3 minus negative 2. So it's just like saying delta x over delta t. So in this case, we've got our values here. We're going to say 9 f of 3. When I put 3 in, 3 squared is 9 plus 3. Minus, when I put in negative 2, I'm going to get 4 minus the 2 all over 5. And this reduces down to 12 minus 2 over 5, which is going to end up being 10 over 5, which is 2. Now this doesn't have units, we're just finding an average rate of change, so we will just keep it as 2. So moving on to the next one, we are going to use the definition of a derivative to find f prime of x. Now, I know we know the shortcut, I know we've covered the shortcut, and we all know that this answer, if I did this using the shortcut, should quickly end up as being 2x plus 5 by taking the derivative. But in this problem, we want to use the definition. We're going to do it the long way. We have to break it down the long way. We've gone over why it's important to know the definition and how we will be tested on it on the AP test. So let's go ahead and apply the definition for this one. And the definition is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. Now, if I had an a value, if I wanted it at f of a, I would go ahead and substitute this and say f of a plus h minus f of a and put in that value because it just simplifies the work a little bit. But in this case, I just want the general derivative, so we're going to walk through the whole problem. So this becomes the limit as h goes to 0, and I'm going to put in x plus h where my x terms are, so I get x plus h squared plus 5 times x plus h plus the 4. Now let's go ahead and subtract by putting in the f of x, which is just our equation, x squared plus 5x plus 4. Be careful with this. Put the brackets here to understand that this negative is going to distribute throughout so that we don't have any issues with a floating negative there. All over the h. Now, continuing on, we end up with the limit as h goes to 0, and we're going to FOIL this whole thing out. So we end up with x squared plus 2xh plus h squared. Now, if I did this correctly for this problem, things should reduce out. Plus 5x plus 5h plus 4 minus the x squared, we're distributing at this point, minus the 5x minus the 4 all over h again. Alright, let's see what reduces out here, what cancels out. Let's see, this x squared with that x squared. We've got this plus minus 4 with this plus 4. Anything else that we could do? We get the 5x with the minus 5x. So it looks like we've pretty much taken care of everything that we could. So we still have the limit as h goes to 0, and now I just have 2xh plus the h squared plus the 5h all over h. Well, they all have an h in common, so let's take that out. So the limit as h goes to 0, and then we end up with 2x plus h plus the 5, and as h goes to 0, we can go ahead and over h, and we reduce it here. Sorry about that. Now, as h goes to 0, we're going to end up with 2x plus the 5 because the h will reduce out. So there is our derivative. Alright, our next problem covers particle motion, and this is the basics as we've started to work with particle motion. So let's move this up over here and take a look, and here's what we got going on. For this one, it says, consider a particle whose motion is represented by this. Let's go ahead and put some units on this since we didn't do that. Let's say that s of t, where t is in seconds, and we'll say that it's in meters. The position. So we have this equation, and t is going to be greater than 0 or equal to 0. So to find the velocity, the velocity is just simply the derivative. So v of t is going to be the derivative of our position equation, our s of t, and in this case we can go ahead and use the shortcut at this point. I didn't ask you to use the definition, so we're going to go ahead and say 8t minus 1. So this is our v of t equation. Okay, now for the acceleration. Well, the acceleration at t is just the derivative of the velocity. We can also say it's the second derivative of the position. So in this case, we end up with simply 8, which is our a of t. Now, we want to know a of 3. Well, a of t is going to end up being a constant for this problem. So a of 3 is just going to be 8. It's a constant. Alright, now we want to find the position at t equals 3. So that's just asking us to find s of 3. And s of 3 is going to end up being 4 times 3 squared. I'm just substituting it into the equation. Minus 3 plus 1. So this just got substituted in our top equation over here. And we're going to end up here, once all of this is cleaned up, 34 meters. Because I asked you to put some units. So let's over here put, this is going to be meters per second. This will be meters per second squared. Alright, so moving on to the next question. It says, find the distance traveled by the particle in the first 2 seconds. So we want 2 seconds how far it's gone. Now, one thing to note here is that if the velocity is positive, that means we're going to be moving forward. If the velocity is negative, that means we're going to be moving backwards. So I can start, say, here and move 1, 2, 3 steps forward, but then 1 step backwards from there. What was my distance? Well, I went 1, 2, 3 plus this one. I traveled a distance of 4 steps. Okay, so what we need to do is we need to take into account the backwards motion. So since we have to do that, we need to find out when is the velocity positive and when is the velocity negative. So when is it moving forward, when is it moving backwards? So here's how we do that. We're going to find out when the velocity stands still. So when the particle is not moving at all, that's what we want to find out. And we solve this, and this happens at 1/8 of a second. So at 1/8 of a second, this particle right here, 1/8, is not moving at all. So if I put in a value greater than 1/8, I'll end up with positive numbers. And if I put in something between 0 and 1/8, because it says where t, it says right up here, where we're only considering when t is greater than or equal to 0, when I put that number in, I get negative. So in this, from 0 to 1/8, in this interval, we are going to be moving backwards. And in this interval, we're going to be moving forward. So what we want to do is we want to break this apart, and we want to find the position at 1/8 minus the position at 0. That'll tell me this distance traveled backwards. And notice I'm taking the absolute value because I just want a distance traveled. I don't want to know where it's at. I just want to know how far it's gone. And then I'm going to go from 1/8. So basically I'm going from 0 to 1/8 and then 1/8 to 2 seconds, because this is backwards and this is forwards, and I'm separating these and adding the two together. So now in this case we're going to go ahead and say, I could put absolute values, but it's not going to matter because I know it's moving forward, so I'm going to get a positive number. We're going to say s of 2 minus s of 1/8. So putting in s of 1/8, put in 1/8 into your equation, and you're going to end up with 15/16. I'm just sparing you the math and details in between. I went ahead and already did this. Minus s of 0, put in 0, you'll get 1. Plus s of 2 ends up being 15. And s of 1/8 we already know as being 15/16. So cleaning this up and working this out, we end up with cleaning this up and working this whole problem out, we end up with 14 and 1/8 meters as the distance that we have traveled. Alright, let's take a look at our next problem. Let's slide this up a little bit here and see what we got. And in this case, I'm asked to sketch a graph of a function with the following properties. And I'm given all this information. I'm giving what f of 0 is, what f prime of 1 is. Look, f prime of 1, this is a derivative. So this is telling me the slope at 1 equals 0. Here's another derivative. The slope at 3 is negative 2. So remember, the derivatives are telling us the slopes at those points. So let's go ahead and put a grid up here and just start plotting some things that we see. I'm going to clean this up a little bit, make this a little bit nicer. So let's go ahead and make this just a little bit straighter. Alright, good enough. So let's see what's happening. At 0, f of 0 is going to be negative 1. So at 0, I'm at negative 1 right there. So I'm going to go ahead and put that point in. Then I'm told that f prime of 1 is 0. Okay, so that means the derivative at 1 is 0. So that means I have a horizontal tangent at 1. So right here, I'm going to just put these little horizontal tangents as my guide. So I know that at 1, this is the slope. I don't know where it goes through right here. This graph can come up from this point. I know it's got to go through this point. It could come up way over here and flatten out, or it could be coming down and flatten out. Let's see what other information we're given, or it could just go straight across. We don't know anything yet about where it crosses here, but I do know that it flattens out right there. So let's go ahead and put in some other points and see what happens. We know the derivative at 3 is negative 2. So 1, 2, 3. Oh, that's a negative 2. So the slope here is negative 2. I'm going to do the same thing that I did over there. I know that it's heading in that direction somewhere at 3. And that's my negative 2 slope. And I just kind of guesstimated the steepness of it because I don't have a nice grid here. Again, if I had a nice grid, I would maybe make that really good slope slanting negative 2. But I don't, so I'm just guesstimating. And on this next one, I've got a slope at negative 1 to be 1. So here's negative 1, and now I've got this slope like this. Again, I don't know where it's going to cross through over here yet. Let's see and what kind of information we're given to try to piece more together. But I can kind of get a general trend that it's going like this, flattening out, then coming back down. I can kind of see that already, that something like that's happening. Goes through this point though, remember, and it's got to be coming up this way, so I'm not going to come down through it. I got to look at the slope here, so I got to come up through this point, flatten out, then go back down. Alright, let's see what else we're told here, and we could do more. Over here I have the derivative at 4 is 0, so back to 4, and I know I'm flattened out again. I've got some sort of horizontal tangent here. Later in the course, we're going to learn that I'm kind of drawing a slope field here. But that's later. Alright, so now, at 4, I have a value of negative 5. So at 1, 2, 3, 4, I've got a value of 1, 2, 3, 4, negative 5. So I do cross through right there. And then the derivative at 6 is 2. So let's go back to 6 here. And this derivative is 2, so I've got a slope that goes back up. So now I can kind of piece this function together. I don't know exactly what it's going to look like, but I can kind of guesstimate that it's going to come up through this point, flatten out, start going back down, has to go through this point, and it flattens out here also, and then comes back up. So this is one possibility for what this graph can look like based on the given information. Alright, moving on to number 5. Take a look here. I've got f of 2, f prime of 2, g of 2, g prime of 2, and I'm asked to find h prime of 2 at h prime of 2 if I'm given the following conditions. So over here I have h of x equals f of x times g of x. So since I want to find h prime of x, I'm going to go ahead and use a product rule, and we know it's going to be the first times the derivative of the second plus the second times the derivative of the first. So put times there. And since I want h prime of 2, let's go ahead and put f of 2 times g prime of 2 plus g of 2 times f prime of 2. And working all this out, I find out that f of 2 over here, taking a look at what I'm told, f of 2 is 5, so I'll go ahead and put in 5. And then g prime of 2, I'm looking at g prime of 2, I get negative 4, so we're going to put in times negative 4. And then we're going to say plus g of 2, which is going to be a value of 3, times f prime of 2, which is a value of negative 1. And that gives me h prime of 2 as being negative 20 minus 3, which will be negative 23. Okay, for b, it says h of x equals 2 times f of x over g of x. So in this one, we're going to use the quotient rule. So I've got h prime of x equaling the bottom, which is g of x, times the derivative of the top. Now, this is a constant, so it's just going to be 2f prime of x, minus the top, which is 2f of x, times the derivative of the bottom, g prime of x, all over this bottom, g of x squared. Now, putting in values I know. So h prime of 2, let's go ahead and put in 2 for all the x's, and this is basically what I'm solving. So 2 times f of 2 times the g prime of 2 all over the g of 2 squared, and that gives me the following. It'll give me 3 times 2 times negative 1 minus 2 times 5 times negative 4 all over 3 squared. Let's slide this up a bit. And that's going to give me negative 6 minus 40, or plus 40, all over 9, which will be 34 ninths. And that's what my h prime of 2 will end up being. Alright, now let's move on to this last one. And in this last one, I've got some other things going on. So let's find out. If I want to take the derivative, h prime of x, this is just a basic derivative. So this is going to be negative 2x. Plus, here I need a product rule. First, times the derivative of the second, plus the second, f of x, times the derivative of the first, which would just be 2. And now here I'm going to take the derivative of that, which is 0, since it's a constant. I need h prime of 2, so I'm going to go ahead and skip a couple steps here, and we're going to just say this is negative 2 times 2 plus 2 times 2, and then f prime of 2 is negative 1, plus this will be 5 times 2. F of 2 comes out to be 5, and then cleaning all this up, I will get h prime of 2 equaling negative 4 minus the 4 plus 10, so h prime of 2 ends up being a value of 2. Alright, let's move on to the next page of this, and let's slide this down and see what we got. Alright, here we are asked to find the tangent line to f of x equals x squared plus 1 at the point 1 comma 2. So, tangent line means we're going to take our derivative. And in this case, I will have to use the quotient rule again. So we're going to say the bottom times the derivative of the top. So this gives me x times 2x minus the top, x squared plus 1, times the derivative of the bottom, which is 1 in this case, all over the bottom squared. So since I need this to happen at x equals 1, I want f prime of 1. And we'll go ahead and figure this out by plugging in 1 into our derivative. And I'm going to get 2 minus 2 over 1, which comes out to be 0. So I have a horizontal tangent, since the slope is 0. So that means I'm going to have a horizontal line. In this case, we can it'll end up being, if we wanted to go y minus y1 equals m times x minus x1. Here our slope is 0. We have x minus 1, and then this will be y minus 2. So we just end up simply with y equals 2 as our tangent line, since we have a horizontal slope. Alright, moving on to the next problem. We want to know for what values of, or where does f of x equal x cubed minus 6 have a horizontal tangent. So this time I'm being asked, where is the horizontal tangent? Well, what happens when we have a horizontal tangent? We know that the slope has to be 0. So let's take the derivative of this, and I'll end up with 3x squared minus 6. I want to know where this is going to be 0. And in this case, I could simply solve it. You could take a 3 out, subtract the 6 over, then divide by 3. It doesn't matter how you solve it, but you're going to get x equals plus or minus the square root of 2. This is where the two values, this equation has a horizontal tangent. Alright, for number 8, let's slide this up. We want to know the derivative of y equals 2x sine x, and then the second derivative of that. So again, that's just Leibniz notations. We know that, so we're going to go and work with that. So we've got dy dx equaling, well, here it's going to be product rule. So we need the first 2x times the derivative of the second, which derivative of sine would be cosine x, plus the second, which is sine x, times the derivative of the first, which will just be 2. Now, you can clean this up. We could leave the answer like this. You can take a 2 out. So we can say you could take this 2 out if you really want to clean it up, and you'll have x cosine x plus the sine x. If it's a multiple choice test, most likely you'll see it in this form. If it's free response on the AP, you can leave it unsimplified like this, unless they ask you explicitly to simplify it. Alright, so now let's take the second derivative. And in this case, we're gonna use this form, this original form here. It'll be easier to work with this one. So what we're gonna do is the product rule in the first part. So first times the derivative of the second, and in this case it'll be negative sine x plus the second cosine x times the derivative of the first, which will just be 2, plus, again, put this 2 out in front. Think of it as 2 sine x, and that 2 is a constant, so we're just going to end up with 2 cosine x. And again, we can clean this up a little bit if we wanted to, and just say that this is negative 2x sine x. Now look, you've got 2 cosine x plus 2 more cosine x. You've got 4 cosine x's. So we could say that this is what our d squared y over dx squared is, so our second derivative comes out to be that. Alright, now moving on to number 9. Let's slide this up, and here we go. We want to sketch the derivative of each of these graphs. On part C, I need to clarify something, so when we get over there, I'm going to clean this graph up a little bit, show you what it was supposed to look like. It's kind of hard to draw these sometimes. So, alright, so let's take a look at this first one. On this first one, the first thing I like to do is I like to look for horizontal tangents, because horizontal tangents tell me that the slope there is going to be 0. These are my 3 horizontal tangents. I'm just going to graph my derivative straight on this graph, and I'm going to estimate it here. I'm not going to find the pure exact. I'm not going to calculate things. I'm just sketching, because it, again, just says to sketch. Alright, so from here to here, let's start in this first section, okay? This value is a horizontal tangent, so I put it at 0. That slope was 0. Now, my slopes are from this point getting larger, larger, larger to about right there. Right there, the slopes change and start to get smaller again, but they're all positive in here. So right at this point, I have a maximum slope. And I'm just going to guesstimate, and I'm going to say that maximum slope hits 1. So the slopes increase to that point, then decrease back down. Similarly, in this fashion over here, these slopes are all negative, and they're getting larger negative to the largest negative slope that you can see, possibly right there. And I'm going to just say it's down here, and then they turn to be positive again. So I'm going to say that right around to right here is going to be my largest negative slope, and then it turns back to be positive. So this goes like this. It curves through here, goes up, and then these slopes all are positive in here. So right at this point, notice here's my horizontal tangent. I'm at 0, and then it goes above the axes because now we've got positive slopes. Here's my horizontal tangent right in here. This is a horizontal tangent. It's at 0, and then the slopes turn to be negative, so I need to be below the axes. So this is the graph of the derivative of part A. Alright, looking at part B, this is a linear equation. It's constant. I can calculate the slope from here. Let's say I've got a point right there. I'm just kind of guesstimating. We're going to go up 2 over 1. So my slope is going to be 2 over 1, which is 2. So this whole graph, we're going to go ahead and put arrowheads on this. Same thing with this first one. Let's go ahead and put arrowheads so we can just be consistent here. So this slope is 2. That means it's linear and constant at 2 throughout everything. It's going to move in that fashion. Okay, let's clarify part C here. This is the intent of this problem. This is supposed to be a kink and a kink, right, in each of those. This is supposed to be linear, and this is supposed to be linear. And this is supposed to be parabolic in between. So we've got linear with a kink, parabolic, kink, linear. That's the way we're going to sketch this. So let's start with what we know, and let's go with the linear part. In the linear part, that means I've got a kink here. So I have an open circle somewhere here. Along this, somewhere right here, I'm going to erase what I drew, but somewhere along here, I've got an open circle. Well, let's see what the slope of this is. If I go from over 1 and down, this slope is roughly, I'm going to guesstimate, look at from here to here, I'm just kind of guesstimating the slope, and I'm going to go down 3, and I went over 1, so we're going to say that this, down 3 and negative 1, so we are going to say that this slope is roughly positive 3. So from here, where the kink is, all the way along this part, we are at positive 3. It's a positive slope, and we are roughly at about 3. Again, this was just a good little guesstimate as to that slope. Okay, so let's go ahead and move on to the next one. Again, this went over 1, left 1, and down 3, so I'm kind of guesstimating that. Let's look at this next kink on this side and this linear part. So I'm going to take a look over here to see what this is. Now, again, I'm going to guesstimate. I'm going to go to the right one here, and it looks like, let's just follow it down to the graph and see where we end up. Well, that one's a little bit steeper. It looks like I'm roughly about right there. So it's a negative slope, so I'm going to go down roughly about 6 over 1. So on this one here, we had a slope of 3. On this one, we're going to roughly estimate this as being negative 6. Let's take a look again. I went over about 1, and we're down here at about negative 6 before it crosses that graph. So that's my guesstimate. If you're off by a little bit, this is not a perfect grid. That's fine. So, but we know that it's negative, so I want to be below the axis, and there is a kink. That's where the kink is, starting from here. So that's where I have an open circle, and everything is going to go this way. Again, this should have arrowheads on it as well. That's my mistake. I should have, when I created this, put the arrowheads on. All right, so now we've graphed the kink part. What's in between? Well, in between we've got something that looks parabolic. So we know that if we are reducing this by a degree with the derivative, it's going to be linear. But we should know this anyway, because here is a horizontal tangent. So at this point right here, I'm going to be at 0. These are negative slopes, so I will be below the axes. These are positive slopes. So let's take a look at that again. These are negative slopes, so I'm going to be below the axes. These are positive slopes, so I'm going to be above the axes. So up to about right here, okay, that's where I want to stop, and it'll go from, I'm going to just kind of graph this in a linear fashion. It'll go up to about there and stop. This will go to about right here and stop. So I've kind of pieced this together. This is my linear function. the derivative of this parabolic in between function, open circles because there's a kink, can't take a derivative there on both sides, and then over here our slopes were positive. That's about how high up they were because we measured this, and these were negative. They went in this fashion, so we were right here. So again, this graph, if you want me to clean it up, let me put another color in here to kind of highlight it a little bit. This graph looks like this: open circle through there like this, and then open circle here, and then at this kink we have an open circle and we go this way. So that should be what this graph looks like for the derivative. Alright, hope this helps. Good luck on your test.